So good morning, everyone, and welcome to the sixth episode of the Facade webinar series. My name is Laetitia Marot. I am a Marie Skłodowska-Curie Fellow at the Inorenew Center of Excellence, and I propose this webinar series in the frame of my facade project that aims at developing a bio-based coating for wooden facades. It's a great pleasure for me to introduce today our speaker, Dr. and architect Salvatore Viscuso, who is going to talk about adaptive facades and their capability to increase the environmental efficiency of contemporary buildings. Dr. Salvatore Viscuso is Adjunct Professor and Researcher at the Politecnico di Milano. He is a doctor in technology and design for environment and building, and his research focuses on the design of innovative building components through computational design methods and novel remanufacturing models of construction materials. Today, the presentation is recorded, and as usual, you can send your questions in the chat on the right of your screen. And I will read them to Dr. Viscuso at the end of his presentation. And if we do not manage to reply to all of them, we will come back to you by email in a couple of days. So now let's talk about adaptive facades. Dr. Viscuso, you can start.
Thank you, Laetitia, for the great introduction, and thank you to everybody to join this webinar. I'm very pleased to let's say disseminate our finding in the research activities here at Politecnico University of Milan. And today I will focus on kinetic architecture, as Laetitia explained very well, for building applications. So I would like to introduce very quickly myself. Okay, so I was able to go on. And this is only a brief introduction of my academic career. I started to work at Politecnico University of Milan in 2012, focusing on a research project for humanitarian sheltering. And we design, let's say, emergency shelters for NGO and obviously affected population. I obtained my PhD degree in 2016. My dissertation was focused on the computational design for building facade. And now I'm working, let's say, here at Polimi on researches for activating circular processes in building construction. So what about adaptive facade in architecture? So adaptive facade are today used for having a better response to the external boundary condition. No? You know that climatic condition can change every day or considering the season. And for this aim, let's say the adaptive facade skin can support the reduction of the energy demand of the building, because they can adapt, let's say, and then they can change the thermal exchange between outside and inside, between outdoor and indoor space, considering, let's say, the boundary condition of the climate. And for activating, for enable, for let's say obtaining this adaptability level, we can let's say manage the material, the construction material, in two principal ways. The first one consider the translation of or the rotation of the construction element, of the construction material, using a hinge or a mechanical system that can move the, let's say, the element of the facade. Another feasible opportunity refers to, let's say, change of the shape of the material itself. And for this, for obtaining this result, obviously, we can work on the elasticity of the material. We are talking about kinematics for the first example, and for the second one, obviously, we are talking about the kinetics properties of the material. Let's say the properties of the material to change the shape, considering, let's say, the elasticity of the material, the stiffness of the material, and the feasible transformation that work within, let's say, the elastic, let's say, characteristics of the material without transforming the material in a plastic way. Okay, so obviously we can collect a lot of case study around the world that use adaptive facade system, and we did a lot of research for collecting all these case studies in a sort of a literature review of this topic in the building application. So let's see together for a few minutes some of these examples. First of all, we will focus on kinematics, so on buildings that present a facade that can change using a mechanical system. The most famous building that works, that use this technology is, you know, the Institute of the Monde Arabe of Paris in France, built in 90s. The architect is Jean Nouvel, but obviously, let's say the case study are also more recent. For instance, this is a building realized in Germany in 2011, in which the facade present, let's say, this vertical shading system that can move around the rotation axis, a vertical rotation axis, using a mechanical and automatic control. We have, again, a lot of case study. For instance, this one is a particular system in which every hexagon of the facade can be closed or open, considering, let's say, a rotation that is, let's say, that work around a rotation axis that is perpendicular to the facade itself. Or maybe you already know this tower built in Abu Dhabi in 2012, in which every facade element is a tessellation of this origami pattern, let's say, that can be closed or open around, let's say, the middle lines that we can draw inside every triangle of the facade. Okay, so I prefer to talk with you, obviously, about the kinetics properties of the building materials, because in my opinion they are very interesting, because we can change the shape of the facade itself, working, as said before, on the elastic properties of the material. This is let's say, an experimental research of Stuttgart, the University of Stuttgart, for realizing a facade system in which every element can be bent for opening or closing the facade itself. The material obviously is a textile material that is very elastic, and along the edges, the architect used, let's say, a bending active material, for instance, a carbon fiber tube. This principle was used also for this building. This is a pavilion built in 2012 for an expo, for the Universal Exposition of Seoul. This is very interesting because, let's say, the principle is the same. We have an elastic material a rigid edge that can be bent in order to open or close every vertical element, such as, let's say, a building's a fish skin, you know. This is another example in which all the stripes can be moved using, let's say, an hinge that allow the rotation of the bottom part and the top part of this textile stripe. You can see also that the architect apply a PV system on this textile stripe in order to increase, obviously, the efficiency of the residential building. And all the system that we saw until now, obviously work with an automatic, with a mechanical, let's say, control system that can open or close the facade itself. But we have to take into account also that we can use smart material, for instance, for realizing passive control system without having, let's say, an active control of the opening or of the closing of the facade. For instance, a lot of research, let's say, tried to link the use of smart material with the biomimetic approach that we can use in architecture. Let's say we can differentiate the biomorphism. Let's say the biomorphism is the reply of the natural shape from the bio-utilization. The bio-utilization, sorry, try to replicate the natural behavior, no, not the natural shape, but the natural behavior of animals or vegetals in nature. So we can study the nature to try to replicate the natural behavior in architecture. And for do that, maybe we can use the smart material in order to activate this passive control system of the opening or of the closing of the facade. For instance, this is, let's say, an experimentation done by Archimedes in 2012, in which this particular facade or maybe roofing system, you know, this is a little example, but this technology could be scaled up to the building scale, no? This is an interesting facade system that can be open or closed considering the humidity level of the surrounding environment. No? The timber is layered in order, using different timber types that are layered one to each other in order to respond to the humidity level of the surrounding environment. And in that way, obviously, the timber can absorb or, let's say, leave water, and changing the, let's say, the level of water absorbance of each material, let's say, every cell can be open or closed considering this particular aspect. And this system was replied, obviously, in other application. This is a pavilion built in France in 2003, and let's say the system is the same of the previous one, no? The 3D element that are realized using a compound within timber, within, let's say, wooden waste, no, wooden byproduct, no? Using wooden byproduct in the thermoplastic compound, the architects printed this little element that can open or close considering the humidity of the external surrounding area. This is another interesting system in which the element of this roof can be open or closed using, let's say, shape memory alloy. No, this let's say element can activate the movement of the facade and roofing element, considering also in that case, let's say, the levels of temperature of the surrounding, let's say, of the context. During the hot season, the shape memory alloy open the canopy, and during the winter, obviously, or when the temperature is lower, the system is closed. But I think that all these elements, let's say all these example, focus our attention to the principal barrier for the, let's say, for the spread of this technology in the built environment. The main problem is that these are complex geometry, right? And it's not so easy to apply these particular technologies in the common construction activities, right? And for this reason, for instance, Renzo Piano, a famous Italian architect, used for the shading system of this building, used normal textile rolls, let's say, for realizing the internal shading system of the facade. Let's say he applied typical industrial component for this shading system. Otherwise, for this building realized in China in 2012, the architect used an adaptive system, not an industrial component, let's say, for realizing this shading, let's say, tessellation of shading element that can be open and closed around the facade, around the, let's say, the dome, realizing in that way an adaptive system that obviously works better than the previous one, in which, let's say, we don't have the same shape, no, for the textile and for the glazing, for the external glazing. For the textile, realize a segmented path, no, and obviously the facade is a curved facade. In that case, we have for both glazing part and textile shading, we have, let's say, a curved path for both systems. So this is the main barrier, again, for the application of this element in the building construction. And we can understand very well that on the left part of the slide, we can see, no, the typical product that are used in the construction industry for realizing shading system. Otherwise, on the right part of the slide, we can see, let's say, an adaptive shading facade, and the difference between the two systems that we are seeing now is large, no? But we have to, let's say, to clarify that the industry works mainly with this type of product, not sure with this one, no? So what we have to do to put closer these two opposite systems that we are seeing in that slide, we have to, let's say, focus on the, let's say, production management of building products. We can see, for instance, that we can talk about the typical, let's say, process of for the fabrication of facade element that works mainly on the early differentiation. Let's say the industry differentiated the product at the beginning of the production chain, no? And he realized different product for several applications. Otherwise, another opposite approach can be used for our purposes in order to realize a product that can be applied differently in several applications. For better understanding this opposite approach, we can focus on the little picture of this slide. On the left part, we can see the facade of the Guggenheim Museum of Bilbao, built by Frank Gehry in the 90s, no? And using an early differentiation approach for the fabrication of titanium panel, no? The problem was that, let's say, the industry doesn't calculate very well, obviously, the tolerance between the element, and the result is, let's say, what we are seeing in that pictures. No, the elements are not so well done, and maybe the shape is not the optimal one for this, let's say, complex tessellation applied in a complex shape. You know that the Guggenheim Museum, the shape of the Guggenheim Museum is very complex. Otherwise, if we use the same element, for instance, this flat triangle panel, metal triangle panel, we can bend, no, this, let's say, this component in order to realize also complex shape. No, you can see, for instance, this element is bent in the picture in order to follow a complex shape for the envelope. So, if we consider a matrix that, let's say, contains the standardized production and the customized production. So this matrix work starting on the left part from the lean models, and gradually go on the right part until a complete agile construction flow. Okay, so considering these metrics that obviously refer to the feasible fabrication chains or models, we should focus on this part of these metrics that refer not to the feasible construction product that can be, let's say, designed and fabricated as make-to-order product. No, we can design a particular customized product and realize this product, maybe use digital fabrication processes. No. What we are seeing in that slide, let's say on the left part of the matrix, we have a typical model that, let's say, can produce an outcome similar to the picture on the left part of the slide. Let's say if we want to standardize the chain, maybe we can realize, let's say, facade element that work within a rigid frame, and obviously this frame can be rebuilt or can be realized only using this order in the tessellation of the part of this facade. Otherwise, on the right part of the slide, we can see a shading system for a building built in Sydney, in which the same element, the same metal element, can be bent differently considering the orientation of the facade. And in that way, we can differentiate the facade itself using a simple cold bending step in the fabrication of this system. Otherwise, the 3D printing represents an early differentiation, no? Because we fix a geometry, we realize a geometry printing it, let's say, in a rigid way, and obviously we can't, let's say, transform or reuse again this element because other, let's say, the shape that the 3D printing realize is a shape that work essentially for let's say a single application, right? On the contrary, this let's say experimental pavilion built in 2011 is very interesting because starting from the same element, from the same metal, let's say, sheet, we can, let's say, assemble differently this metal element in order to create a complex geometry, as the geometry that we can see in the right part of the slide. But in addition, let's say, also in that case, we can figure out a layering, no, a multi-layer of metal sheet, no, of thin metal sheet, in order to create a system that can be open or closed, considering the, let's say, the humidity or the temperature or the boundary condition of the context. Because the different metal layer have a different, obviously, let's say, properties. And for this reason, the layering of different material can be realized a passive control system for opening or closing the facade element, considering the humidity and the temperature of the context. Another feasible option is, let's say, to use the digital fabrication for bending the element, let's say, considering the path that can be bend the element itself. In that slide, we can see, for instance, in the animation, how is it possible, no, to figure out, to predict the path that the robotic, let's say, machine should use for bending the sheet and obtain a particular shape for the metal sheet. No, every part for every part we can figure out a different shape of the metal sheet. And we can do the same, obviously, with the timber. We already saw some example of timber, let's say, adaptive facade. This is another interesting example that show us how we can bend, you know, the laminated timber, the thin laminated timber. And in that way, we can realize, also in that way, we can realize complex geometries starting from the same flat element. This is a typical example of delayed differentiation or postponed differentiation. That is the opposite of the 3D printing or the other production chains that works on the early differentiation. And obviously, in that way, we can reduce a lot the production cost, because we can work with standardized element that can realize customized shape. Okay, we can do the same, obviously, using textile or other flexible material, you know. But I want to focus now the attention in the last part of this lecture on some concept that we did within our research here at Polimi. This is a facade system that we designed for the Expo of 2015 in Milan. This facade system works, let's say, uses textile and a path that we applied to the textile for realizing this honeycomb 3D element for the facade that we can stretch, no, differently on the facade itself. So also in that case, a standardized production can be stretched differently in the facade in order to adapt the component to the shape of the facade itself. We can see here other picture, but I mean, I want to focus your attention on the amount of the material that is very low if we compare it with the amount of material of normal facade system. This is a facade, textile facade system built in Riyadh in 2013. If we calculated the material, the amount of material needed for building this facade, we have, let's say, more material compared to our concept, and we have also more packaging volume to transport all the element on site compared to our concept. This is another interesting pavilion that we built, in 2019 here at Politecnico di Milano. This is, let's say, bending active arch, that a series of bending active arches that are put one to each other, close to each other in order to realize a tunnel. Okay, in that way, bending differently, the bending active arch, we can cover different internal area. Also in that case, we can talk about adaptability, because we can bend differently, and in that way we can enlarge or reduce the internal area of the tunnel. And obviously we can, let's say, adjust the bending of the arch working on the cable, on the strut system made of cable that is put below the carbon fiber arch. Okay, the same principle was adopted for the research of the humanitarian application, the research that I explained here at the beginning of this lecture. For instance, this is a concept for a roofing system that can be adapted to different shapes, closing or opening the folding lines that is, let's say, applied on the tarpaulin in this part that using this part that you can see here in the picture, and folding or closing, let's say, this folding part, we can obtain different shape, and we can link the final shape of the roof to the archetypical shapes of the roof of the affected population. This is the, let's say, the prototype that was built and was used in Senegal for 4 years, if I remember well, in a refugee camp. Okay, the final project that I want to show you before closing this lecture is this interesting textile shading system that we, let's say, use internally in the castle, in the city castle, Castello Sforzesco of Milan. Obviously, this shading system is indoor, is applied inside. But the main issue, the main challenge of this project was that we can't use, let's say, or we can't fix this shading system to the surrounding masonry, to the surrounding walls of the window, because let's say the castle is an historic, an historic building, and we can't, let's say, create holes on the wall, or we can fix the element of the shading system to the wall directly. And for this reason, we use also in that case a bending active system, in order to, let's say, push the textile shading system to the external wall. And in that way, we fix the system without using a screw or without creating hole on the wall itself. obviously we started to study, let's say, to characterize the textile for, let's say, studying the daylight of the indoor space. And this is the final result that we build, and currently these windows, all these windows of this room in the castle of Milan are shaded with this system that we design and we realize, obviously with an industrial partner that support us. Okay, so I finished my presentation. Maybe I talked more than the time that was assigned to me. I would like only to thank, let's say, the cost action, novel structural skin, and the research project Renetta that, let's say, allow me and all of us, all my research group, to realize, to have this literature review and to realize these prototypes that we saw in the final part of the lecture. This is our research group, let's say the project that I show now, our project, let's say, that involved all of us, and you can see the link of our website here on the right, in the bottom part of the slide. But this is, let's say, a screenshot of our website, and you can find additional information about our project in the, let's say, in the website itself. And finally, okay, I would like to present, let's say, my last publication is an Italian book. I apologize for that, but I'm confident to translate everything in the following years and publish the book also in English. The book refers to the agile design in architecture and building construction. And let's say, I think it's enough, and I would like to thank you again for the attention. Thank you.
Thank you very much, Dr. Viscuso, for your interesting presentation. And I think it's very good that you highlight that it's one thing to think about the conception and the materials, but also it's very important to anticipate an easy realization of the facade and to think about scaling up in the early stages of the project. Also, congratulations for your book. I would be very happy to practice my Italian to try to read it. We have some questions in the chat. So the first one is from Václav, is saying that passive self-actuating system employ thermal or hydral expansion depending on the material chosen. That's what you explained during the presentation. Are you aware of any facades utilizing both, so combine hydral and thermal system by joining the two different materials, causing a synergetic and maybe more effective actuating effect?
Yeah, it's a good question, because it's right. Let's say I simplify a lot, but some of this system works on, let's say, works on considering the humidity, you know, of the environment. Other system works on the temperature changes. And okay, if we want to think a system that can integrate both, let's say, both conditions, I think that we have to integrate, you know, a system that use a different layering of the material that maybe, let's say, can change the shape considering the humidity changes, together with a system that work, for instance, with shape memory alloy, you know, that can change the shape of the material itself considering the temperature changes. Okay, so honestly, I don't know a system, also from the experimental point of view, a system that is trying now to integrate both, let's say, both feature, both both aspects, but maybe there's something also that is moving in that direction, and I don't know, for instance, and I didn't see the finding of this experimentation. Um, Please consider that every year the Stuttgart University or other let's say architecture university that works on these topics, for instance the Institute of Advanced Architecture of Catalonia. Okay, every year these universities realize pavilions, experimental pavilions that works with this principle, and maybe the research in the following years will try to combine, both aspects for the self-actuating, for realizing a self-actuating system that take into account both thermal and hydral, let's say, changes of the shape of the for changing, sorry, the shape of the building elements. But the example, obviously, the example that we saw today works or on the hydral expansion or on the thermal expansion.
Mm-hmm. Okay, thank you. There is another question from Victor Bukowski. He would like to know if you encountered thoughts of designs where the facade responds to occupant behavior or occupant needs in any way.
Yes. Okay, so obviously for realizing a passive system that take into account also the occupancy, of the building, we have to understand and we have to let's say focus on the let's say on the aspect that could change, the shape considering the occupancy. For instance, one feasible aspect can be again the temperature or the humidity of the indoor space, and in that way we should design the control system, the passive control system, in order to refer to the indoor condition, humidity or temperature, that obviously depend from let's say the occupancy of the indoor space, the number of users, or let's say the time schedule of the occupancy itself. You know that today maybe it's possible also to let's say create a monitoring system of the occupancy level using the digital technology. For instance, we can count the number of the people that are inside an indoor space using a system that count the people, but otherwise in that way we are creating an active system, not a passive system. We have to pay attention that if we create a mechanical system or digital system that link the facade activation together with the number of the user, we are creating an active control system. If we want to focus our attention only on passive control system, obviously we have to work with let's say with the level, with the building physics input that we can assign to our passive system. And until now, the research focuses essentially on humidity, and on temperature. It's very difficult, for instance, to say, okay, the daylight should be the 20% in this room, in the room of my office, okay? But how to control the opening or the closing of the shading system if we want to obtain the 20% of the light, without using mechanical element or let's say an automatic control system. it's quite impossible to work essentially on, let's say, a passive control system without having, in that case, a mechanical hinge, for instance, or a system that is literally, in other words, inactive system. Because if we want to control the daylight, we have to put a sensor that controls the daylight, and considering the data that the sensor registers, we can activate the closing or the opening of the facade itself. It's not possible until now, for instance, create a passive system for the daylight. It's possible to create a passive system for temperature and humidity, because we can control the change of the shape of the material, considering the properties of the material itself. Okay, what about the maintenance? Obviously, these systems are not so simple for the maintenance point of view. Obviously, the facility manager don't like this type of element, but the idea to standardize the product and obtain a different customized configuration with the same product maybe can let's say support the service life, let's say, of the building component, because of the building system, let's say, because when we have to substitute as let's say an element, we can let's say find very simply the substituted element if every building element is standardized. This is the reason why, in my opinion, it's very important to start from standardized element and then obtain a customized configuration during the installation, because in that way we can recover from the market very easily another piece, or we can substitute the element without realizing, without fabricating a new element with, let's say, customized dimension. Okay. Otherwise, if we adopt, for instance, a facade with elements that are 3D printed, when we have to substitute an element, we have to print a new component that is not available on the market. And this is the reason why, in my opinion, we have to postpone the differentiation in the last stage of the production chain in order to use standardized element coming from the industry in a customized way. In that way, in my opinion, we can also, how to say, support and make more easy the maintenance itself of the facade.
Okay, I understand. Then thank you very much for replying to the questions. Thank you again for your presentation. Thank you to all the participants who joined us today. And I hope you enjoyed the webinar, and I hope you will come back to see one of the future webinars. So have a great day. Bye and take care.
Okay, thank you to everybody. And for any question, any doubt, obviously, as Letizia said before, maybe you can contact me also by mail.
Yeah.
Have a nice
Thank
day.
you. Bye.